So welcome back. So we continue with the exploration. Am I audible? Hello?
Yes, sir.
Okay.
Yes, sir.
Fine. Thanks. So we stopped by saying that there is a relationship between two different matrices which represent the same linear transform. In fact, we see that we have plenty of choice of representations for a linear transformation in terms of matrices. So which one to choose? Obviously, we would choose the simplest matrix, but in what respect? Simplest matrix in what respect? First of all, it has to be non-trivial. It is not a zero or the identity matrix, but something else which can possibly represent it, but it's not trivial. You see that the criteria that we choose is that the matrix operation has to be simple. You know that matrices can be added, matrices can be multiplied, and addition is it's a simple operation, whereas multiplication is a very complicated operation. And you see that if A n by n matrix A is given and another n by n matrix B is given, AB is calculated in a particular way. So also BA can be calculated, and you know that in general AB is not equal to BA. All these properties are there. I don't have to go into that. But you see that among all matrices, you find a diagonal matrix, something particularly simple. What do we mean by a diagonal matrix? So A is said to be diagonal if A, which is written in the form Aij, is diagonal if Aij equal to 0 whenever I is different from J. So the matrix takes a form actually something like this. A11, A22, ANN, or we can rewrite this in the form where lambda I equal to I. Now the advantage that you have is, suppose you have two such diagonal matrices, then their product is essentially another diagonal matrix where you see that the ith element of the product is the product of the ith elements of the two matrices. So if you have A diagonal, or I would put it this way, I would use lambda 1, lambda 2, lambda n, etc. So choose the let lambda be lambda n and or A equal to this, B equal to P1 UN then AB is lambda 1 mu1 lambda n. In other words, it is easy to multiply these such matrices. For example, if you want to write down a polynomial in PA becomes simply P0 into I plus P1 A plus P2 A square Pn a to the power n or m. Em a to the power n. And this actually takes the form of a diagonal matrix, which is given by P lambda 1 P lambda n, where P is given by P0 plus P1 T plus etc. So that is, of course, a great advantage that we have of diagonal matrices. So the question that you want to ask is, given a linear transformation, is it possible to find a diagonal matrix to represent it? So let us ask the following. If yes, then we have a wonderful result. Okay, but unfortunately, it is not always true. Okay, but we will do an example to highlight this point. Right? Now I'll give an example where it is. Yeah, okay. But before we do that, we have to do some exercise. So we look forward to this. But how do we investigate this? Because you see that we have to find an isomorphism. So the question, see, the problem is now find an ordered basis or equivalently an isomorphism that will postpone the general question. Is it possible? Does there exist an existence problem? We just put off for the time being. And then we investigate. Suppose it is possible. Then, is there any way to find the ordered basis which facilitates that? See, it's not an easy problem. The forward problem was very easy. I mean, always the inverse problems are difficult. The problem that we have addressed is this: how to find a diagonal, how to find an n by n matrix which represents a given linear transformation. That's fairly simple. Choose any ordered basis and write down the matrix representation for that. But now what we are doing, we are asking for is something more. We are asking for a representing matrix to be of a particular type, say diagonal. So essentially, you have to hit upon an appropriate, a choice of an appropriate ordered basis. Is it possible? Or how to get hold of that, even if we know that it is possible. Okay. So let me just make a note of it. What's the problem in this? There exists a that's the first question. The second problem is if yes, if there exists a diagonal form, how to find it? That's all. How to find out this? So if you want to find this out, you have to have fixed isomorphism from X to Fn. But how to fix the isomorphism? That's the problem. Okay. You know that the isomorphism, fixing the isomorphism correspond to choosing an ordered basis. Therefore, I can retranslate the question as how to find a suitable. Okay. If P admits a diagonal representation, the isomorphism which is facilitated. That's the question. That is how to find an ordered basis. Let us investigate this. Okay. So my next task is investigating this. So let us explore this problem. So what would let us once again go back to our figures. X to X. You have from what we do is we choose an ordered basis. Now we have seen that the way in which we have chosen it. Okay. Isomorphism. Phi. Then we have phi x I equal to E. This is the crucial observation, which implies xi equal to phi inverse of E. So let us have this. Because it's an isomer, this is what we look at. Now suppose the linear isomorphism phi produces a then we have lambda of EI equal to lambda I. Okay. So what do we have? Okay, now what happens? Let us look at the action. So you see that lambda EI. What is lambda? Lambda is equal to, first apply phi inverse, then apply, okay. First apply phi inverse, then apply T, Then apply phi. This is your lambda. Okay. Interesting. Let's apply phi inverse T. So what do we have? I have lambda EI equal to phi T phi inverse EI, which is equal to EI. Therefore, I get phi inverse of lambda EI equal to T phi inverse of EI. Therefore, lambda I phi inverse of EI equal to T of phi inverse of EI. So you have the following relation: T of xi equal to lambda I xi. Okay, where xi equal to phi inverse of EI. What does this relation mean? It says that, see, we said that the ordered basis can be constructed if we hit upon these xi's. Okay. Now, what is this? Suppose the representation is diagonal given by lambda. Then you see that each xi is the action of t on each xi is amounts to just scalar multiply it. This is a special vector. Okay. Or you see that solution of the equation Tx equal to lambda x for lambda equal to lambda I. Where you know these lambda i's are not arbitrary numbers, but they are numbers which come from the diagonal representation. Okay. What is it means? That is each eigenvector, or what you call a characteristic vector, P belonging to belonging to the eigenvalue lambda I, one characteristic value. And this is one big observation that we make. So we hit upon what is called an eigenvalue problem. What is the eigenvalue problem? Given T, lambda is said to be so when you consider the equation, X is called the eigenvector. So that's the definition of eigenvalue and eigenvalue. Now, how to find the eigenvalue of an eigenvalue of? That's the next problem. How to find observe. In lambda belonging to F, T minus And t minus equal to 0 has x equal to 0 as a solution for a free. However, for certain values of lambda, this happens. Not one to one. These are all the various terms of singular. So we are not interested in so the question is, which lambdas Suppose it's an n by n matrix. Then matrix representation of T minus lambda I is given by A minus lambda I. Where I is the n by n matrix. Okay. So the question is, so the equivalent question is, for what not invertible. Okay. If V prime is another order basis, for X and B is equal to T B prime, then lambda. Okay. And inverse. Now you see that A minus lambda I is invertible if and only if B minus invertible. So A minus lambda I is singular, and we also know that determinant of C inverse and determinant of C And of course, C is invertible, therefore so the consequence is that P minus lambda I is invertible. Or we have A minus lambda I is singular. So T minus lambda I equal to 0. That is T minus if and only if determinant of zero. This is something that we say for the time. And I think that's a nice place to end this talk, because we are now approaching or almost converging to a method of finding out an eigenvector. You know that eigenvector is essentially a solution of the equation T minus lambda I x equal to 0. It is such solutions exist if T minus lambda I is singular for a particular lambda, and such values are called the eigenvalues. Okay. So once you get the eigenvectors, you stand a chance of getting an ordered basis with respect to which possibly if you get sufficiently many vectors to span your space, then you have a chance. If you get n vectors, n linearly independent vectors, which are eigenvectors of T, that would form a ordered basis for the vector space, and with respect to which P is the ideal. Now, this is our strategy. So, I think we will stop here for the day and then continue with it in my next lecture, that is sometime next week, next Saturday. Thank you very much. Okay, we'll stop here. Right.
Thank you, sir.